Alright, so we've gone over discrete math from like the permutations, combinations, and Pascal's triangle standpoint on the memorization / study guide sheet. And that looked like this right here. So permutations and combinations, and then we had binomial theorem and Pascal's triangle. So we're going to look at a few examples of what these actually look like. If we have one red dog, one brown, and two white, and 4 kennels, how many different ways can we create this situation? I'm going to interpret this as a permutation because I do think order matters. I think it matters where our dogs are going. You know, those 2 white dogs aren't identical. They're just both white dogs. So that outcome, or the order, does matter. And there are 4 kennels. However, there are duplicates. So if we're going to look at this, there is n factorial over k1 factorial, k2 factorial, etc. And that's our permutation formula for when we have duplicates in our choices. We have equal slots. So we have 4 factorial, and then we have 1 red dog, so that's 1 factorial. We have 1 brown dog, that's 1 factorial, and we have 2 white dogs, so that's 2 factorial. 4 times 3, and then we'll just leave this as 2 factorial to drive home this point. It's not enormously helpful in this problem, but when you have huge factorials, it makes sense to be able to cancel them at that point rather than write them all the way down. We wind up with 4 times 3, which is 12. So there's 12 different permutations that we can create, and like I said, I decided this was permutations by the fact that those 2 dogs are not actually identical. The point I was trying to make with this is, if we had a situation like 10 factorial over 9 factorial, that's going to be really annoying to write all the way out. So instead, we could do 10 times 9 factorial, that's the same thing as 10 factorial, over 9 factorial, and these would cancel, leaving us with 10. That's much faster. With that being said, let's take a look at another one. Let's use our dogs and kennels again. So if we have 1 red dog, 1 green, little kid dyed it, 1 brown, and 1 black. So we have 4 dogs, and let's say we have 3 kennels available. Actually, let's take that even further. Let's say we have 2. How many different permutations can we create? So this is 4p2, and our formula for this, because there's no duplicates, n minus r factorial is this. So we just plug in. We have 4 different dogs, and 4 minus 2 factorial And again, 4 times 3 times 2 factorial over 4 minus 2 factorial. Turns out there are 12 ways to do this as well. So depending on the situation with like duplicates and whatnot, the permutations can change, right? There's only 2 kennels in this problem, whereas before there was 4 kennels. So onwards to combinations then. So in this one we're saying that like a pepperoni sausage pizza is the same as a sausage pepperoni. There's no difference. I love using food for this because it seems to make sense when we have something that's blended together. So let's say we have a blended drink. And we have options: apples, oranges, pears, grapes. Oh, sorry, I forgot I was just using letters. And milk. And we are going to use 3 ingredients. That's going to give us a combination of 5, pick 3. If you remember our formula, it's going to be n factorial over n minus r factorial r factorial. So let's plug in, because we need to account for right here that the ordering no longer provides a separate result. So that's why we have another r factorial down here. So that's going to be 5 factorial, 5 minus 3 factorial, 3 factorial. So again, didn't want to write it all out. That's a waste of time. We cross those 3's. 2 factorial is actually just 2. So what we're going to get is 20 over 2, which is equal to 10. There are 10 different ways to make our blended drink. There's one more type of combination that we're going to talk about, and it is the situation where you can pick up to a certain amount of ingredients for that. So let's use the same one. Let's say we've got apples, oranges, pears, grapes, and milk as our options. But we don't have any limitation on our smoothie. It's up to 5 items. In that case, for every item, you have a choice: yes or no. Right? All the way down. In that case, our answer then would be 2 to the n, right? 2 being the yes or no, and n being how many ingredients we can use, and we can use up to 5. So if we have 5 ingredients, that would mean we can get 2 to the 5th, which is 32. So 32 different smoothies can be made with just these 5 ingredients. And as I mentioned before, that's how like a lot of those sandwich places and whatnot say, like, oh, we've got hundreds of different sandwich options available. Yes, but I mean, take that with a grain of salt to what that actually means. Next, let's take a look Pascal's triangle and binomial theorem. So if we're going to draw Pascal's triangle, that's what we should do first. We're going to put 1, and then that's row 0. So this is going to be our rows out here. And you add the number before it. So if this is row 1 then, well, if we look to the upper left and upper right and add, there's nothing here, so that one's going to become 1, in the same situation with this one. Then we have row 2. Again, on the outside, there's just a 1 there. There's a 0 here, so that's just going to be a 1. But here we have a 1 and a 1. That's going to create 2. And then 1 on the outside here, same situation above. And we just keep continuing this pattern. 1, 1 and 2 makes 3. 2 and 1 makes 3. 1, that's going to be row 3. For row 4, 1, 4, 6, 4, 1. And so forth. So that is our Pascal's triangle. So now let's take a look at binomial theorem. So there's this right here, this complex way of writing it, where you're taking, from where k equals 0, we're going to take the sum up to n pick k, x to the n minus k, y to the k. So let's take a look at what that actually means when we put it into practice, and it's actually far less complicated. Let's start with x plus y squared. So this will be an easy way to see how this operates. So we're going to look at the second column. That's where our leading integer is going to come from. So our first integer is going to be 1. And then we're going to have, I don't actually need this. We're going to have x to the, remember that k is equal to 0, so we're going to have n minus k, right? So they're just going to go in reverse order. 2 minus 0 is just going to be 2, and then when k is 0, that'll be 0. So what this ends up looking like is 2 minus 0, y to the 0, plus 2, x to the 2 minus 1, y to the 1, plus 1, x to the 2 minus 2, y squared. So as k increases, right, for y, then the exponent of x decreases because that's also going to be where k goes. So k goes in both spots. And it just literally means that 1 is increasing while 1 is decreasing by 1. And then the leading integers all come from the power. So if we're looking at a power of 2, then we use the second row. So 1, 2, 1, 1, 2, 1. And then we can actually work this out. So 1 times anything is itself, that's going to be x squared, y to the 0 is going to be 1, plus x to the 2 minus 1 is just x to the first power, so that's going to be 2x and then y, plus 1 times anything is itself, x to the 2 minus 2 is x to the 0, which is 1, and then we have y squared. So this is what we ended up with as an answer. Well, this is actually pretty easy to multiply out. So the reason for Pascal's triangle binomial theorem is for really high powers, but since this is really low, we can actually test this and make sure that it worked out correctly. X times x is x squared. X times y is xy. Y times x is xy. And y times y is y squared. Combine like terms, x squared plus 2xy plus y squared. Those are the same answer. It works. So let's try this with something a little bit more robust than just a quadratic, because that's a little too simple for using this anyways. Let's take 2x plus y, and since we've got an integer here, this actually be a little bit more complicated anyway, so we'll just put it to the third. So in this case, using the third row of Pascal's triangle, so the leading term is going to be 1 times, now be careful here, because when we look at this, n minus k, b to the k, 4a plus b to the n. When we look at this, some people get confused and just think that, oh, that just means x, and that's the only thing that power is hitting. No, this could be any term. So a, in this case, is being represented by 2x, so it's 2x to the n minus k, which will be 3 minus 0, and then y to the 0, plus 3 times 2x to the n minus k, pick 3 again, and then 1 to finish. 2x, 3 minus 3, y cubed. So, again, the main thing I want to point out here is that if you have a situation where it's not just x or not just y, that power needs to be applied to the whole term, not just the x. So let's work this out then. We have 2x to the third, that's going to be 8x cubed, and then times 1 here and times 1 here is just going to leave us with that, plus that's going to be 2x squared, so that'll leave us with 4x squared times 3 is going to give us 12 x squared, and then that's just y, plus 2x to the 3 minus 2, so that's going to be to the first power, so 2x times 3 is going to be 6x, then we have y squared, plus 2x to the 3 minus 3, that's going to be 0, so that'll be 1 times y cubed. And we're done. So as you can see, like as we would get into higher and higher binomial expansions, this would become fairly difficult to do longhand. So this is the combination of these two things allows us to have a trick to getting there quicker. And with that, that should do it.